And I've been using what we call Hayworth projections. It's kind of what I prefer, kind of simplifies things a little bit, makes it a little bit easier to see. So in Hayworth projection, we're eliminating the any hydrogens, which is quite common, of course, but we're also really kind of simplifying the structure. And the reason Hayworth projections are useful because it's very clear to identify. So if we look at alpha D glucose here, this is carbon 4. It's very clear to see that that hydroxyl group is pointing down in a Hayworth projection. In a chair here, carbon 1, here's 2, 3, 4. I guess it's clear that that hydroxyl group is down. But this one, yeah, I guess that one's going up. It's a little harder to see in the chair that that's going up. And so in a Hayworth projection, it's very obvious that that is up. So it might seem like Hayworth projections are fantastic, and they are for drawing. However, recognize that this is not reflective of reality, right? The sugars are not planar. This looks like it's all in one plane, like a benzene ring or something, and that's not the way sugars are in reality, right? In reality, they're gonna form chairs, like you see with like cyclohexane, for example. So my recommendation is, if I task you with drawing a sugar, draw it as a Hayworth projection, because there's going to be no ambiguity in terms of up versus down. And it can be tricky drawing these things on a test, and maybe things are crooked and all weird, but it's very clear to indicate up versus down. So I tend to use Hayworth projections when I draw stuff. We'll have examples that are both. Now, what I want to point out is a standard representation. And so let me just number the carbons here. 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. Notice that in this particular orientation, when we kind of put the ring oxygen in the back in both cases, and that we are numbering these in a clockwise direction, right? In both cases, we're going around that circle, and the carbons are numbered in a clockwise direction, and that we're kind of viewing this from the top, right? We're kind of looking down on these as if we are sort of above them and numbering clockwise. That's what we call the standard representation, or what I call the standard representation. Okay, so that becomes important. So most of the time when we're learning things, I'll probably have them in the standard representation, but we might see a few things that are not in the standard representation, so we have to adjust some of our definitions accordingly. And so just a couple of points then. The DL designations, if you may have noticed, all the sugars that we've seen, when we're looking at the reference carbon, so carbon number 5, that's here and here, notice that the group going from carbon 5 up to 6 is up in both of those structures in this standard representation. That is an indicator that this sugar, both of these are D sugars, which we certainly expect for D-glucose. So if the bond from carbon 5 to carbon 6 was going down in either of these, and we were still numbering those carbons in a clockwise fashion from above, then those would be L sugars. But like I said, most of the time we're going to be dealing with the D sugars. And so then also alpha and beta, here's kind of some of the important take-home messages here. And I've bolded and underlined things, so that tells you how important they are. As far as the alpha or beta configuration, that's actually dependent on the configurations at both the anomeric and the reference carbons. And so if you just follow this, if the anomeric and reference carbons have different configurations, one is R, one is S, one is S, one is R, then the sugar is going to be alpha. But if they have the same configuration, both R, both S, then the sugar is beta. It turns out the way these sugars are structured, we can also replace this R and S with up and down. So a sugar is alpha if the group at, say, 5 to 6 here is up and this one is down. So up and down, that's two different things. That's going to be alpha. If instead both groups were up, that would be beta. So that's kind of one way to think about it. So that is the real definition, has to do with R and S. But the definition I give here is probably easier to understand and will work pretty much all the time. So if we're talking about common D sugars, like glucose, if the hydroxyl group at the anomeric carbon points down in this Haworth projection or chair, then it's the alpha anomer, right? If it's pointing up, it's the beta anomer. And so that's what we had seen before when we cyclized those sugars. Again, this is all assuming that we're looking at the standard representation. So if the sugar's upside down, we have to kind of think about that definition and how to look at that. All right, so a couple other things about these sugars. As far as because they can cyclize, guess what? Things in biochemistry are reversible, so they can uncyclize. And there's actually a dynamic equilibrium of forms of glucose. So what I'm going to do is draw like a very simplified, almost silly version of glucose. Where I've got the ring oxygen, and I've got the 6-hydroxyl group coming off, right? Kind of like a flag. And then I've got the hydroxyl group off the anomeric carbon kind of going down like that. You can draw the full version if you want. I just kind of want to highlight the more important parts of this. So this, because the hydroxyl group is down, and we're talking about a D sugar, right? This is alpha D. I'm going to use the abbreviation GLC for glucose. Well, that ring formed through the cyclization reaction. Well, guess what? That can unform, right? So we can go from that alpha glucose to the linear Fischer projection, which I'm just going to simplify kind of like that. Right, so indicating 6 carbons. This is the linear D-glucose. Notice that I can't call that alpha or beta, because alpha or beta doesn't mean anything with a linear sugar. You only get that designation after you've cyclized it. Well, guess what then? That sugar can then, it could potentially reform alpha, but now it can actually flip that bond between 1 and 2 and produce the beta anomer. So we can end up then with this. Instead of the hydroxyl group going down, it will go up in this position. And then this is beta D-glucose. This process of converting, actually I'm going to use a different color to show this. This process of this interconversion overall is known as let me spell that more clearly, mutarotation. So interconversion between alpha and beta anomers is called mutarotation. And we're going to see how that's important in a little bit. Another term that's important, pyranose and furanose. This has to do with the number of carbons the number of atoms in the ring. Okay, not just the carbons, but also the oxygen. So a pyranose will have a 6-membered ring, whereas a furanose will have a 5-membered ring. So just to be clear, when we've shown a few of these back here, right, here is a glucose is a 6-carbon compound, and there happen to be 1, 2, 3, 4, 5, 6 members in the ring. So this is a pyranose ring. Okay, but I'm going to go back to this slide. Here's fructose. Fructose is a 1, 2, 3, 4, 5, 6 carbon sugar, but notice the ring only has 1, 2, 3, 4, 5 members in it. So although this is a hexose, it is in fact a furanose in this form. So just be sure that you're not confusing the number of carbons with the number of members in the ring. And so in fact, we might use very specific terms. So rather than just saying glucose, we can be very specific. We might say something like glucopyranose. Right? So now we've specified that it's glucose, but also that glucose has formed a 6-membered ring. Or we might use the term fructofuranose as we've drawn. So these are the actual kind of true long names for the things that we've drawn. It's fructose, but it's in a furanose, a 5-membered ring. And it turns out that 5 and 6 carbon sugars, pentoses and hexoses, the geometry of the way that the ring forms, you can actually form both furanoses and purinoses from them, but most sugars typically exist in one form over the other. So for example, glucose is actually greater than 99% purinose. Now fructose can form purinose and furanose, and in fact in water the purinose form, the 6-membered ring, is a little bit more common, but it turns out the furanose form is the biologically relevant one, so that's the one we spend a little bit more time on. Now rings that are larger or smaller than 5 or 6 aren't as stable, so we don't really see them very often, so we're typically only going to see furanoses and purinoses. A couple last topics here. The conformation of the sugar and also pucker is an important thing to consider. You learned cyclohexane and cyclopentane, and sugars kind of can do some of those same sorts of things. So if we look at beta-D glucose, for example, notice I can draw 2 different conformational isomers. Like no bonds have been broken, right? These are just bond rotations that enable us to go between these 2. Now if you think about it, notice that in the one here, right, that CH2OH group is equatorial, and this hydroxyl group is equatorial. All these hydroxyl groups, in fact, are equatorial in beta-D glucose. However, notice that in this other conformational isomer, that the CH2OH group is axial, and in fact all of those hydroxyl groups are axial. So you remember this from cyclohexane. The more stable thing to do is to put those bulkier groups in equatorial positions, because it kind of spreads them out around the equator rather than bunching them up in the axial direction. So I think we all can agree that this form is more stable, and because of that, this is going to be the more favored form. We're going to see beta-D glucose in solution is going to exist in that more commonly. And again, these are conformational isomers, so you should be able to kind of see rotated bonds and things like that. There was no breaking or anything of bonds to go between those 2. All right, the last topic is modified sugars. And this is where things can change. We can, not all sugars have just hydroxyl groups, but there can be some modifications to them. So, for example, we can make amino sugars. There is this sugar called glucosamine, which becomes important in various parts of biology. And notice that it has a hydroxyl group that was at the 2 position, is now gone, and it's replaced with a nitrogen. And we see this thing in cartilage. We see it in bacterial cell walls. We also see it in chitin, which, if you recall, is fungal cell walls and insect exoskeletons. Chitin gets modified a little bit from there. But this is going to change things, right? This is an amino group, and it's going to carry a positive charge at physiological pH. So that's going to change properties of how that sugar behaves. Another one is glucuronic acid. Glucuronic acid is present in connective tissue. And notice that it is a more oxidized form of glucose. So a lot of things on here look similar to glucose, the positioning of those hydroxyl groups, but we actually, carbon 6 here, is oxidized to form a carboxylic acid. And of course, carboxylic acid in physiological pH, right, that's going to be negatively charged. It's going to deprotonate, and that's going to change its properties a fair amount, so that can carry a negative charge. Another one that we observe a lot of is deoxygenation, just removing an oxygen. So a deoxy sugar, 2-deoxyribose, you know that is from DNA. And then there are some other goofy sugars. Humans are kind of boring, but it turns out bacteria do lots of cool things. So this sugar called desosamine is heavily modified. Notice it's missing a hydroxyl group off the 6 carbon and the 5 carbon. At position 4 here, it's been replaced Of course, it had an OH group, but now it has this dimethyl amino group. So very much heavily modified. Humans don't really do stuff like this, but bacteria do. And in fact, what we observe is erythromycin is a antibiotic compound that contains this desosamine sugar right there. It's kind of in a wonky position, but try to convince yourself, find the anomeric carbon, number the carbons if you want to. Good practice. It's in a kind of upside down like configuration. Also contains this other unusual sugar called cladnose. Turns out that erythromycin needs these sugars to be present in order to be an effective antibiotic. It's actually enabling the binding to occur. So now I just want to show you the strategy for drawing a sugar, and I would encourage you at this point to pause the video and just give this a shot on a scrap paper or something. But try to draw beta-D glucopyranose 1-phosphate. And so I'll go ahead and do that and show you my strategy of how I go about that. So the first thing I look at is what type of ring am I going to draw? And so first I see that I need to draw a pyranose ring. So to draw a pyranose ring, I will start with the horizontal line, and I'll put an oxygen, and then so I'm going to do this in a Haworth projection, and then I'll put another line parallel to that, and then I'll connect these two like this. And so you can kind of see how I have formed a 6-membered ring by doing that. So then the next thing I'll look at is the reference carbon. Is it D or L? So this says D, so remember in a standard cyclized sugar that this bond here is going to go up. So I've got this, and that's going to be an OH like that. So this is what I would call the D pyranose core. Now this is glucose, and so glucose is going to have a particular configuration at the 4, 3, and 2 carbons, and we have to know what that is. Now we can go in our notes, we can look it up, we can look at the Fisher projection, we can look at a Haworth projection elsewhere in the notes. But one trick to remember about glucose is it has this every other up-down kind of pattern. So I'm going to start and kind of go backwards here. Notice that from 5 to 6 is up. Well, glucose is stable and it spreads things out. So at 4, this is going to be down. At 3, it's going to be up. At 2, it's going to be down. So they alternate, down, up, down. So remember that. So I'm going to draw this one down. Carbon 3 has a hydroxyl group going up, and carbon 2 has it going down. So now we've got most of that glucose drawn. So we got the gluco part kind of taken care of. And then we have to pay attention to this phosphate and this beta. And so now we're just waiting to see how that gets attached. So remember, beta means that the configurations at the reference carbon and the anomeric carbon, which is going to be here, are going in the same direction, up in this case. So beta tells us we're going to draw a line up like that. Now, as we'll see, this phosphate is a modified sugar, and the way that this would get added, it's going to get added to the hydroxyl group. So don't draw this, but if we were just drawing beta-D glucopyranose, I would have that right there with that hydroxyl group going up. But we're not just drawing that. We're going to instead have a phosphate group there. And so phosphate, as you recall, will look like this. And depending on the pH, these are probably going to be negatively charged like that. So notice there's this oxygen right here used to be the hydroxyl group, and we've added PO3 to it, and we'll talk more about phosphate chemistry later on. But please recognize, don't draw this. We would never see anything like this, where we have a hydroxyl group in addition to that phosphate. That's a really bizarre thing, so we wouldn't see that. So please recognize that we're modifying it at the hydroxyl group, so get rid of that. The other thing, recognize that we would never have a situation where we have 2 oxygens bonded together. So if we had, say, the anomeric carbon here, we had a hydroxyl group, we would not want to ever draw anything like this. Okay, I can't even look at that, it pains me. So notice we've got these two oxygens bonded to each other. That wouldn't happen, so please don't do that. I got to get rid of this stuff, it makes me nervous to see it.